All right, so this is Module 5, and in this module we talk about energy flows and feedbacks. So mainly we're going to talk about power, energy input, systems that require power, energy, some measurements that we use for power and energy, and then we'll touch a little bit on the thermodynamics. All right, so energy, just some definitions, but energy is the ability to do work. We measure that usually in joules. A joule would just be the amount of energy that we use when 1 watt of the device is turned on for 1 second. And then power is the rate. So like how much per time. So here's kind of how we calculate energy. Energy is just simply power times time, whereas power is energy divided by time. So how much energy do we use per hour, per minute? That would be power. And so I just listed here some common, let me move my little video, some common units that we use. So calorie, notice how there is a lowercase calorie and then there's an uppercase calorie. So they mean different things. One basically is looking at food energy, and then the other one is how much energy does it take to heat 1 gram of water. So we'll refer to both, and then we look at BTUs. BTUs is a British thermal unit, so we use that to measure the energy put out by water heaters, things like that. So we'll use a variety of things this year in this unit, anyways. And then kilowatt hour, so how much energy expanded for 1 hour. So how much kilowatts power do we use for 1 hour? So that would be a kilowatt hour. And that's what City of Reading measures your electricity bill in, if you ever were to look at that eventually in the future, I guess. But that's what they measure in. So BTU is like, sometimes we use that for propane, something that we're measuring out like that. But kilowatt hours is what City of Reading uses. And we will, like I said, we'll practice calculating in a variety of things. All right, so a few more definitions here. Most of these should be review, probably from chemistry. But when I refer to electromagnetic radiation, I'm just referring to sunlight, basically. So all the different energy forms that come from the sun. And then a photon is just that packet of energy that comes from the sun. And that's what the electromagnetic radiation is made out of photons. Potential energy is energy that is ready to be used. So think of like a battery, for example. Think of your muscles, with stores of glycogen in them. It's ready to be used. Chemical energy is stored in chemical bonds. So this oftentimes is from food, where we get our chemical energy. And so we eat the food, and then that's stored in our muscles for potential energy. And then kinetic is moving. So moving energy would be kinetic. So if I'm using energy right now to do this lecture, then that's kinetic energy. It's my potential energy that's being converted into kinetic energy. And then temperature is simply just the average kinetic energy of that substance is what all that is. All right, so a couple questions to ponder. How does the amount of solar energy in a system determine the suitability of an environment for growing food? So I'll give you a minute to think about it. So think about here. So if it's too hot, like a desert, we also have to have water. If we don't have water, then it doesn't matter how much sunlight we have. If we have a forest, like super dark, we're not going to be able to grow crops that require lots of sun, like corn or wheat or things like that. So the amount of energy is definitely really important, the amount of solar energy, but also water. That's a huge factor. And then where would there be more or less chemical energy ultimately available if there is less solar energy? Well, chemical energy is stored in plants, for example. So if there's less solar energy, as long as let's say there's an abundance of water. So the more solar energy, the more chemical energy we can have, because we have plants converting electromagnetic radiation into chemical energy. And so if we have less solar energy, pending that there's the same amount of water, then we're going to have less chemical energy as well. And that's just because plants require sunlight. All right, so the first law of thermodynamics basically states that energy cannot be created or destroyed. It can only be changed. So if we think of this car, energy input is going in, and so we've got potential energy. It could be the gasoline. It could be a battery if we're using an electrical car, electricity. So it goes in. And then out is the waste energy. So that could be heat, that could be the carbon monoxide, dioxide. It's the movement, the friction of the tires. So all of that is output. So we look oftentimes in systems with the energy coming in versus the energy going out. And then the conservation, the last little part at the bottom, conservation of energy within a system. And that's basically, in cars, if we look at potential energy, we want to maximize the conservation of energy. We don't want to waste that at all. And so we look at better design and aerodynamics, better fuel efficiency, less drag from the tires, all kinds of things. So we definitely want to conserve energy, but it's not all conserved. It's some of it is lost to heat and things that we don't want. So those are things that we don't desire, but it's just inevitable. All right, and then the second law of thermodynamics is just saying that basically there's less and less energy available as it's transformed. So it loses its ability to do work. So if we look at this diagram, we've got the factory, and then we've got heat energy being lost, a lot actually. So 65% of the energy in this factory is lost as heat. And then only 35% of it is going to the electrical grid. And then through that, there's friction, of course, again. So we've got about 10% here being lost, 90% going towards the light bulb. And then with an incandescent light bulb, which are totally inefficient, there's a lot of heat. So if you've ever touched one, they get very hot very quickly. So that's why LED is really nice, because it really doesn't give off a lot of heat energy, and they're very, very efficient. So with this incandescent, you have heat, 95% lost, only 5% is light. Very non-efficient. So that's the second law, just basically states that it becomes less and less efficient as you go on, because a lot of it is wasted into the environment. All right, and then also with this second law, there's some other terms that go along with it. So we look at efficiency. So how efficient is something? So energy efficiency is it's going to use an amount of energy, but is it going to waste it? So the LED light bulb, for example, it puts out the same amount of lumens. So lumens would be the amount of light, but you've got way less heat being generated, so you've got way less waste. And then they're also, because of that, the way they're made, they use a lot less wattage as well. So so it puts off the same amount of light, but saves you a tremendous amount of lost energy. And then energy quality. What kind of, where we get our energy from? Are we getting it from gas, wood? Are we burning coal? What are we doing? And so the quality is really important, because as we learn later on, pollution is pretty bad for the environment. And so, especially air quality and all kinds of things. So definitely the quality of our energy is really important. And then entropy, randomness. So the second law states that there's less and less energy. There's also more and more disorganization. So that's entropy. And entropy is always increasing. So as energy transfers from one system to the next, it is changed and not as organized. And so on the bottom of the slide, it says, name an example of entropy in your life. So think about something that gets more and more unorganized as time goes by. I can think of one in my house would be my kid's bedroom, which I'm sure you're probably is the same way. So it's hard to keep things clean, because things get more and more disorganized as time goes on. And then you have to spend the weekend or whatever cleaning it. So, so that would be an example of entropy, but energy does the same. All right, so if we look at matter and how energy flows through a system, that's really important to scientists, especially environmental scientists, because we need to know how it flows in the environment, to study the environment and how the ecosystem and everything interacts together. So think about, why is it important to look at a whole system rather than only the parts of the system? So why wouldn't we look at just one part? Like, for example, the positive and negative feedbacks that you guys are looking at in class. So why don't we just look at like a small little portion? Why do we look at the entire picture? So if we look at the entire picture, we can see maybe the variables that go into that and how that might factor. But if we don't, if we just look at one little portion, then we don't see the big picture. And then we can't see maybe there's variables coming in from this area and this area, and we can't figure out how it works together. So we have to look at the whole system. And that's really hard sometimes. I mean, sometimes the whole system is the Earth. And so there's a lot of variables in the Earth. And so it's extremely important that we do that we look at the whole system. All right. So there's a couple of different types of systems. I talked a little bit about this in my earth science class. I'm not sure where a lot of you are coming from. Some of you are in my class, but open system and closed system. So open systems are where matter and energy can exchange. So think of the ocean, for example. So water can evaporate, it can rain, things can go in, we can take fish out, energy goes in and out freely. So that's an open system. A closed system, a good example of this is a jar with a lid on it. So sometimes closed systems can allow energy in, but not matter. Matter can never, and a closed system never go in and out. Sometimes energy depends on what we're looking at in the closed system, but a true closed system would be no energy or matter. A semi-closed system would be no matter escapes or enters, but energy can. So the Earth, for example, is considered to be a closed system. Energy can come in and out, but for the most part, matter doesn't. Sometimes we might send astronauts out or something, but that's really not natural. For the most part, it's closed. Every once in a while, a meteorite may come into the Earth, but still it's not that often. So it's considered a close. So just think of something that is closed, like a lid. And then input, we look at inputs and outputs of a system, what's going into the system, what's going out of the system. And then we analyze that, and we want it to be in a steady state. So we look for systems, or we want anyway, systems to be in a steady state. So looking at this example here, let me move my little picture. So this is a steady state. So this bucket has holes in the bottom and the water is going out, but the water is coming in at the same rate. So even though it's losing matter, it's losing water, it's still at a steady state. So it's at equilibrium, and that's important in an ecosystem. All right, so I'm not going to have you do this in your lab group, but we're just going to kind of talk about some of these. So this is mainly from when I do notes in class. So if we look at some of these things, I wanted the groups to think about input versus output. So an input to a system, like let's say, for example, humans, group 5. So humans, they eat food, we eat food, and then we go to the bathroom, we breathe, we exhale, we have heat on our bodies. So those are all outputs. And inputs more so would be water, air that we're breathing. So all of these things are inputs, and then we've got the outputs. A bank, we've got inputs. If you're thinking about the money part of it, so money comes in, money goes out. Those are inputs, outputs. And so all of these things have their own inputs and outputs. So if we think of it as a system, our inputs would be, if there's inputs and outputs, then we have an open system. And so if we look at energy and matter in these two diagrams, we have energy going in, and then we have, in this case, outputs would be heat, energy, reflected light. So think about global warming, what you know about global warming. So in a steady state, input coming in would equal output. If that doesn't happen, then the Earth is either going to get colder, if we're thinking about global warming, colder or warmer. So that would be energy. So in an open system, we've got energy and matter going in and out. In a closed system, matter is not going anywhere. So this is why the Earth is essentially considered a closed system. It depends on what you're looking at. So if you're looking at energy, it's not. If you're looking at matter, it is. So it can be either open or closed. But just realize that when we're talking about open, usually we're talking about matter. Energy, not so much, but matter coming in and out, that would be an open system. All right, so in class, we also looked at positive and negative feedback. And so positive feedback, remember, it has nothing to do with being good. Positive feedback just means that it's continuing to escalate or continuing to get worse or even better. It could be getting better, but negative, negative impact would be then that it's going back to its steady state. So let's look at these examples. So lake level. So we're talking about like Mono Lake, for example. So lake level is dropping, and that reduces the surface area. So that means there's less evaporation. So then the lake level rises because there's less evaporation, and then the lake level tapers off. And then this is the positive, where we have population is increasing. And we have, so as population increases, there's more births, right? Or more, I guess you'd start here, but more births. Population increases. And then you have more births because now there's more people having babies. So population increases, and therefore there's even more births. And it just keeps getting bigger and bigger. So the Earth continues to get more and more people all the time. It's grown, I think, 300 million or something like that in the last year. So it's pretty significant, the amount of people that the Earth is adding every year. So that would be definitely a positive feedback loop. It's not positive like in terms of it's good or bad, but it's just positive, meaning that it's continuing to increase or escalate. Whereas negative is it goes back to that steady state. All right, so thinking about these, I mentioned Mono Lake. So Mono Lake is, that's exactly what occurs at Mono Lake. So you've got lake level decreasing, less surface area, less evaporation, and then in the winter months it fills, and so on. And then positive feedback loop on that same example was the human population. All right, so why do you think it's important to study variations in natural systems over space and time? So why can't we just study something right now, like the steady state, what's happening to the ecosystem right now? So think about it for a second. So if we study parts of something right now, so if we were to look at the Earth right now, not knowing the history of the Earth at all, we would think everything's great. Climate's normal, things are normal. Air pollution's always this way. I don't know. So we definitely have to study it over time and see how it occurs or how it changes. Because if we look at like CO2 levels, for example, CO2 levels have been much higher in the past before humans were even here. But we also today are increasing CO2 levels faster than what is normal. So, we need to study, what has happened in the past with high CO2 levels, what could happen in the future. So it's important to study how it changes over time. Otherwise, you wouldn't have any kind of basis on what's occurring. All right, and then this last one, you can answer this on the own notes part. So on Module 5, you have the own notes. At the end, the little box. So I want you to pick your 2 favorite cars, look up the miles per gallon, and then I want you to calculate. So calculate the amount of gas you would need to go from LA to New York. So for example, if it gets 20 miles a gallon, not very good, but if it gets 20 miles a gallon and it takes 200 miles to get somewhere, then you could be able to calculate how many gallons you would need. Of course, it's not going to be that less or that little because you're going from LA to New York. So just look that up on Google Maps, how many miles that is. And then convert the gallons used to kilowatt hours. So I gave you the conversion. 36.6 kilowatt hours is equal to 1 gallon of gas. Okay. And then calculate the pounds of CO2 produced for the drive in number 3. So how much CO2 are you going to use when you're driving to New York? And then just put that in, put this calculation in your own notes, and that'll be good. All right, and that is it for Module 5.